Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're lying exactly where you belong. Horizontal, cozy, maybe with a pillow wedged at that specific angle only you understand. And above you, if the ceiling were to simply dissolve, you would be staring into a blackness so vast, so profoundly old, that every single pinprick of light reaching your retinas left its source long before you were born. Some of those photons have been travelling for 13 billion years. They have been sailing through the void since before the Earth existed, before the Sun ignited, before our entire galaxy finished assembling itself, and now, finally, they end their journey by landing on the back of your eyeball while you're in pyjamas. Congratulations. You probably won't survive the existential weight of what we're about to discuss tonight, but at least you'll be comfortable. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you feel like it, drop a comment with your location and what time it is where you are. I always love seeing how many different corners of the planet are quietly tuning in at the same hour, all of us staring at our screens in the dark like some kind of gentle global conspiracy. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You've heard of the James Webb Space Telescope. Of course you have. It has been splashed across headlines, painted onto coffee mugs, and turned into memes featuring cats sitting on golden hexagons. But here is the thing most people miss when they scroll past another pretty space photo. What James Webb is actually showing us is not just beautiful, it is terrifying. Not terrifying in the way a horror movie is terrifying, with jump scares and bad lighting. Terrifying in a quieter, deeper, almost philosophical way. The kind of terror that seeps in slowly when you realise the room you thought you were standing in is actually a hallway. And the hallway is actually a corridor. And the corridor stretches so far in every direction that the concept of walls becomes meaningless. That is what JWST has done to our understanding of the cosmos. It has removed the walls. Before Webb, we had a reasonably comfortable picture of the universe. Big, sure. Expanding, yes. Old, absolutely. But manageable, at least conceptually. You could hold the numbers in your head if you squinted hard enough. 13.8 billion years old, a few 100 billion galaxies, the observable universe stretching about 93 billion light years across. Those are big numbers, but they are still numbers. Your brain could file them away in the same drawer where you keep facts about dinosaurs and the depth of the Mariana Trench. Impressive, but handleable. Then James Webb switched on its infrared eyes and looked deeper into the cosmos than any instrument in human history, and the universe looked back and said, essentially, you have no idea what you're dealing with. The galaxies were bigger than expected, they were older than expected, they were more numerous than expected, they were forming faster than any model predicted. And the light pouring into Webb's detectors was coming from so far away, from so far back in time, that it predated the era when galaxies were supposed to exist at all. Scientists, and these are very calm, very measured people who use phrases like statistically significant and further analysis is warranted, started using words like impossible and crisis. Not in press conferences, mind you, but in their papers, in the margins of their data, in the quiet hum of late-night Slack messages between research teams spread across 4 continents. Something was not adding up, and the thing that was not adding up was quite literally everything. You see, every point of light in the night sky is a message from the past. Light travels fast, about 300,000 kilometers every single second, but the universe is so staggeringly large that even at that speed, light from distant objects takes millions or billions of years to reach us. When you look at a star, you are not seeing it as it is now. You're seeing it as it was when that light left. You are a time traveller every time you glance upward, and you did not even need a blue phone box to do it. Now multiply that principle by the power of the most advanced space telescope ever constructed. JWST does not just see stars, it sees the ghosts of galaxies that burned and died before our own sun was a glimmer in a collapsing cloud of hydrogen. It captures photons that have been stretched by the expansion of the universe itself, their wavelengths pulled like taffy from visible light into infrared, carrying information about a cosmos so young it had barely learned how to make stars. And what those photons are telling us is that our textbooks need rewriting. Not in a small way, not in a let's tweak this paragraph way, but in a foundational ground floor we might have the story wrong kind of way. Historians of science still argue whether paradigm shifts happen gradually or in sudden ruptures, but what is unfolding right now feels distinctly like the latter. The data is piling up faster than the theories can adapt, and every new observation cycle from Webb delivers another surprise that makes astrophysicists quietly set down their coffee and stare at their monitors a little longer than usual. Here is a quirky detail you probably have never considered. The gold coating on each of Webb's 18 mirror segments is so thin, about 1,000 atoms thick, that if you gathered all the gold on the entire telescope and melted it down, you would have roughly enough to make a single marble. A marble's worth of gold, and it is reshaping our understanding of everything that exists. There is something almost absurd about that, and you're welcome to smile at it as you sink a little deeper into your blankets. Tonight, you and I are going to walk through what JWST has revealed, piece by piece, image by image, mystery by mystery. We will start with the telescope that came before it, the one that first cracked open the door, and then we will trace the insane journey of building Webb, launching it on a rocket on Christmas morning, and parking it at a point in space where it will never ever come home. The story of James Webb does not begin with James Webb. It begins with a telescope that, for 3 decades, was the undisputed champion of deep space photography, a machine so iconic that its name became synonymous with cosmic wonder itself. You know it already. Everyone does. The Hubble Space Telescope, a school bus-sized cylinder of mirrors and instruments that was hurled into low Earth orbit in April of 1990, and proceeded to fundamentally alter humanity's relationship with the night sky. But Hubble's origin story is, frankly, embarrassing. When it first opened its eye 540 kilometers above the Earth, the images came back blurry. Not artistically blurry, not soft-focus portrait blurry, but genuinely, catastrophically out of focus, like someone had smeared Vaseline on the most expensive camera ever built. The primary mirror, it turned out, had been ground to the wrong shape. The error was tiny, about 1/50th the width of human hair, but in the world of precision optics, that is the equivalent of showing up to a piano recital and discovering your instrument is missing half its keys. NASA became a punchline overnight. Late-night comedians had a field day. Congress grumbled about the $1.5 billion that had apparently produced a very expensive piece of orbital modern art. Then, in December 1993, astronauts aboard the Space Shuttle Endeavour performed one of the most extraordinary repair missions in the history of spaceflight. They essentially gave Hubble corrective lenses, an instrument called CoStar that compensated for the flawed mirror. The fix worked, and when the first corrected images came back, the joke stopped. Because what Hubble could see, when it could finally see properly, was astonishing. But the image that truly changed everything came 2 years later, in 1995, and it was the brainchild of a single stubborn astronomer named Robert Williams. Williams was the director of the Space Telescope Science Institute at the time, and he had a radical idea that most of his colleagues thought was, to put it politely, a waste of precious telescope time. He wanted to point Hubble at nothing. Not at a nebula, not at a star cluster, not at a galaxy. At a patch of sky so dark, so apparently empty, that you could hold a grain of sand at arm's length, and it would cover the entire area he wanted to observe. A speck of darkness near the Big Dipper, where nothing interesting appeared to exist. His colleagues pushed back. Telescope time on Hubble was, and still is, among the most competitive scientific resources on the planet. Researchers submit hundreds of proposals every cycle, and most are rejected. The idea of burning 10 consecutive days of observation staring at blank sky felt, to many, like scientific vandalism. But Williams had the authority to allocate a portion of directors' discretionary time, and he used it. He pointed Hubble at the void and told it to keep its shutter open. What came back is one of the most important photographs ever taken by our species. The Hubble Deep Field, as it became known, revealed approximately 3,000 galaxies crammed into that tiny, supposedly empty patch of sky. Not stars, galaxies, each one containing hundreds of billions of stars, some of them so distant that their light had been travelling for over 10 billion years. In a piece of sky so small you could cover it with a grain of rice held at arm's length, there were 3,000 entire galaxies stacked behind one another like pages in a book that stretches back to the beginning of time. You're lying there right now, and above you in every direction, in every seemingly empty gap between the stars you can see, with your naked eye, there are galaxies. Thousands upon thousands of them hiding in the dark, too faint and too far for your eyes to catch, but absolutely, undeniably there. The Hubble Deep Field proved that the universe is not mostly empty with scattered islands of light. The universe is packed. It is absurdly, overwhelmingly full. And here is the detail that really gets under your skin. Williams took that image by pointing at what he believed was a boring, featureless patch of sky. Later deep field observations, the Hubble Ultra Deep Field in 2004, the Hubble Extreme Deep Field in 2012, pointed at different patches and found essentially the same thing. Galaxies everywhere, in every direction. No matter where you look, if you look long enough and deep enough, the universe is teeming. There is a quirky footnote to this story that rarely makes it into the documentaries. When the Hubble Deep Field image was first released to the public, it was printed and hung in the hallway of the Space Telescope Science Institute in Baltimore. Staff members would walk past it every day on the way to the coffee machine, and more than one researcher reportedly admitted that for the first few weeks, the image gave them a low-grade, persistent sense of vertigo. Not from the science, but from the feeling, the raw, gut-level sensation of looking at a photograph and understanding, truly understanding, that the universe was orders of magnitude larger and more populated than the human brain was designed to comprehend. Scholars still argue whether Hubble's deep fields represent a statistically fair sample of the universe, or whether cosmic variance, random, large-scale clustering, might skew the count. The debate gets technical and involves a lot of error bars, but the central finding has held firm. Extrapolate those deep field galaxy counts across the entire sky, and you get a number somewhere north of 200 billion galaxies in the observable universe alone. More recent estimates, folding in the small, faint galaxies that even Hubble could not detect, push that number above 2 trillion. 2 trillion galaxies, each with billions of stars, each star potentially hosting planets, and Hubble, magnificent as it was, could only see so far. Its visible light and near ultraviolet instruments were powerful, but they had a fundamental limitation. The most distant, most ancient objects in the universe have had their light stretched by cosmic expansion into wavelengths that Hubble simply could not detect. Infrared wavelengths. The light was there, streaming through the cosmos, carrying secrets from the dawn of time, but it was invisible to Hubble's aging eyes. Scientists knew, even as they celebrated Hubble's triumphs, that they were only seeing part of the picture. the really ancient stuff, the first galaxies, the first stars, the era when the universe was still assembling itself from primordial chaos, was hiding just beyond Hubble's reach, glowing in infrared wavelengths that required a completely different kind of telescope to capture. A telescope that did not yet exist. A telescope that would take decades to design, nearly die a dozen political deaths, and ultimately become the most complex scientific instrument ever placed in space. You already know its name. And the story of how it was built is almost as wild as what it found. You would think that building a telescope, even a very fancy one, follows a fairly predictable trajectory. You design it, you fund it, you build it, you launch it. Perhaps there are a few hiccups along the way, a delayed shipment of titanium bolts, a software glitch that takes a weekend to fix. But the James Webb Space Telescope did not follow a predictable trajectory. It followed something closer to a fever dream, a 25-year odyssey of engineering brilliance, bureaucratic near-death experiences, and the kind of budget overruns that make accountants physically unwell. The concept that would eventually become JWST was first proposed in 1996, just 1 year after the Hubble Deep Field blew everyone's minds. A committee of astronomers gathered at the Space Telescope Science Institute and asked a deceptively simple question: what comes after Hubble? The answer, they decided, was a telescope optimized for infrared light, one that could peer deeper into the universe than anything before it, capturing the faint heat signatures of the oldest, most distant objects in existence. They called it the Next Generation Space Telescope, which sounds like something out of a science fiction franchise, and in many ways it was. The initial budget estimate was around $1 billion, which in the world of flagship space missions is already a staggering sum, but was considered reasonable for what they were proposing. The timeline called for a launch sometime around 2007. You can already feel where this is going, can you not? That $1 billion estimate would eventually balloon to nearly $10 billion. The 2007 launch date would slip to 2011, then to 2014, then to 2018, then to 2020, and finally to late 2021. At multiple points during those decades, Congress came within a hair's width of cancelling the entire project. In 2011, the House Appropriations Committee actually voted to zero out Webb's funding entirely. The telescope was saved only by a fierce lobbying campaign from the scientific community and a last-minute reprieve in the Senate. The reason for all the delays and cost explosions was not incompetence, it was ambition. What the engineers at Northrop Grumman and NASA's Goddard Space Flight Center were trying to build had never been attempted before, and nearly every component required inventing new technology from scratch. Start with the mirror. Hubble's primary mirror is a single piece of glass, about 2.4 meters across. Impressive, but Webb's designers wanted something far larger, 6.5 meters in diameter, to collect enough faint infrared light from the edge of the observable universe. A mirror that size cannot fit inside any existing rocket fairing, so they did something audacious. They made the mirror out of 18 separate hexagonal segments, each about 1.3 meters across, designed to unfold after launch and lock together in space with a precision of roughly 1/10,000th the width of a human hair. Each segment is made of beryllium, a lightweight metal that holds its shape at extremely low temperatures, and each is coated with a layer of gold so thin it is almost metaphysical. Why gold? Because gold is exceptionally good at reflecting infrared light. It is not there for decoration, although you have to admit it looks spectacular, like a giant honeycomb built by bees with a taste for luxury. That gold coating, as we touched on earlier, totals about 48 grams across the entire mirror. A golf ball weighs about 46 grams, so the most powerful space telescope in history is essentially gilded with slightly more gold than a golf ball. There is a quiet comedy in that. the kind the universe seems to specialize in. But the mirror was only half the engineering nightmare. The other half, arguably the more terrifying half, was the sunshield. JWST's instruments need to operate at temperatures around minus 230 degrees Celsius, just a few dozen degrees above absolute zero, because the telescope is looking for infrared light. Infrared is essentially heat radiation. If the telescope itself is warm, its own heat would blind its detectors, like trying to stargaze with a flashlight taped to your forehead. So the engineers designed a sunshield the size of a tennis court, made of 5 ultra-thin layers of a material called Kapton, each layer coated with reflective aluminum and treated silicon. Stacked together but separated by gaps, these 5 layers work like a cosmic parasol, blocking sunlight and allowing the cold side of the telescope to plunge to those absurd cryogenic temperatures. Here is a historical fact that puts the engineering in perspective. When the Apollo astronauts travelled to the Moon in the late 1960s, the heat shield on their command module was designed to withstand temperatures of about 2,800 degrees Celsius during re-entry. That is one thermal challenge. Survive extreme heat. Webb's sunshield faces a different but equally demanding challenge. Create extreme cold in the blazing environment of space, where the sun-facing side reaches about 85 degrees Celsius, while the shaded side drops to minus 233. The temperature difference across the sunshield is over 300 degrees, and the whole thing is thinner than a human fingernail. And all of this, the 18 mirror segments, the 5-layer sunshield, the secondary mirror on its deployable boom, the instrument module with its 4 sophisticated detectors, had to be folded up like the most consequential piece of origami in human history, packed into the nose cone of a rocket, launched into space, and then unfolded autonomously for the course of 2 weeks while hurtling toward a point 1.5 million kilometers from Earth. There would be no repair mission. No astronaut with a wrench could reach Webb at its destination. If a single motor failed, if a single latch stuck, if a single cable snagged, the whole $10 billion project could be reduced to the most expensive piece of space debris ever created. Scholars and engineers still argue whether the decision to make Webb so mechanically complex was a stroke of genius or a gamble that simply happened to pay off. Some within NASA advocated for simpler, more modular designs that could have been serviced robotically. Others insisted that the science required this exact architecture, with no compromises. The debate shaped internal NASA politics for over a decade, and there were moments when the tension between fiscal conservatism and scientific ambition very nearly killed the project altogether. But it survived, somehow through sheer stubbornness and the collective will of thousands of engineers, scientists, and yes, politicians willing to fight for it. The James Webb Space Telescope was completed. By late 2021, it was sitting in a clean room in French Guiana, folded and packed and ready. And the people who had spent their careers building it were about to face the most nerve-wracking event of their professional lives. A Christmas morning launch, with 344 things that could go fatally wrong. Christmas Day, 2021. Most of the planet is unwrapping gifts, arguing about whether the turkey is dry, and falling asleep on couches in front of holiday movies. But in Kourou, French Guiana, a small coastal city nestled against the northeastern edge of South America, hundreds of engineers and scientists are not celebrating anything. They are standing in control rooms, sitting at consoles, pacing hallways, and doing that particular thing humans do when the stakes are impossibly high. They are being very, very quiet. The Ariane 5 rocket stands on the launch pad at the Guiana Space Center, and perched inside its fairing, folded like a butterfly that has not yet decided to open its wings, is the James Webb Space Telescope. $10 billion, 25 years of work, the careers of thousands of people, the the scientific hopes of an entire generation of astronomers. All of it balanced on top of a controlled explosion that's about to happen in the tropical morning air. You might wonder why Christmas. The launch date was not chosen for symbolism. It was the result of years of delays, scheduling conflicts, weather windows, and the particular orbital mechanics required to send Webb on its journey to Lagrange Point 2. The fact that it landed on December 25th was coincidence, but it gave the whole event an almost mythic quality, as though the universe had a sense of theatrical timing. And in a quirky twist of fate, the Ariane 5 rocket was a European Space Agency vehicle, meaning that the most ambitious American space telescope ever built was launched from South American soil on a European rocket. International cooperation at its most beautifully tangled. The launch window opened at 7:20 a.m. local time. The countdown proceeded without incident, which in itself felt like a minor miracle given how many times this moment had been postponed. Weather delays, technical reviews, a clamp band issue, even a communication disruption. Every one of these hiccups had pushed the date further and further until it seemed like the universe itself was testing humanity's patience. But on that particular morning, the sky was clear, the systems were green, and at 7:20 a.m. precisely, the Ariane 5's Vulcan 2 engine ignited, followed by its twin solid rocket boosters, and the whole assembly rose from the pad on a column of fire and noise and accumulated human anxiety. You can find the launch footage online, and if you've ever watched it, you know it is not the liftoff that gets your heart rate up. Rocket launches, as spectacular as they are, have become almost routine in the public imagination. What makes the Webb launch uniquely nerve-wracking is what came after. The 29 days of deployment that followed, during which the telescope had to unfold itself in the vacuum of space with no margin for error. Here is where those 344 single-point failures come in. A single-point failure is exactly what it sounds like, a mechanism or component that has no backup. If it fails, the mission fails. Period. Most spacecraft are designed to minimize single-point failures through redundancy. You build two of everything, so if one breaks, the other takes over. But Webb's design was so complex, so tightly packed, so fundamentally dependent on mechanical deployments that had never been attempted in space, that 344 of its mechanisms had no backup. 344 moments where the entire mission balanced on a single hinge, a single motor, a single latch, doing exactly what it was supposed to do in the freezing, irradiated emptiness of space. The deployment sequence began almost immediately. About 27 minutes after launch, the solar array unfolded, the telescope's only source of electrical power. If that had failed, Webb would have been dead on arrival, a gilded coffin drifting silently toward its destination, with no ability to communicate, orient, or do anything at all. It deployed successfully. Engineers exhaled. Then came the high-gain antenna, which allows Webb to send data back to Earth. Then, over the following days, the sunshield began its agonizingly slow unfurling. This was the part that kept people awake at night, sometimes literally. The 5-layer sunshield had to be released from its folded configuration, tensioned into its final shape by a series of motors and cables, and separated into its 5 distinct layers with precise gaps between them. Each layer is thinner than a human hair. Each one had to be pulled taut without tearing, without snagging, without tangling with the others. The whole process took about 8 days, and during that time, mission control at the Space Telescope Science Institute in Baltimore operated in a state of controlled dread that one engineer later described as the longest week of his life, except it was 8 days. There is a historical parallel that some people draw to the Apollo 13 mission in 1970. when an oxygen tank explosion turned a lunar landing into a survival crisis. In that case, the danger was acute and immediate. Astronauts were in mortal peril, and engineers had hours to improvise solutions. Webb's deployment was a different kind of crisis. It was slow-motion suspense, a 2-week-long breath hold where every successful step was celebrated with quiet relief rather than cheering, because the next step was already beginning and it carried its own set of risks. Astronomers still debate whether the decision to proceed with such a high-risk deployment architecture was justified by the science, or whether future flagship missions should adopt more conservative, serviceable designs. The success of Webb's deployment has for now validated the bold approach, but many in the engineering community point out that success does not retroactively eliminate risk. It simply means the dice landed favourably. After the sun shield, the secondary mirror swung into position on its long boom. Then the two wings of the primary mirror, those beautiful golden hexagons, folded into place, locking together with a precision measured in nanometers. Each of the 18 segments then spent weeks being individually adjusted by tiny actuators on the back, nudging them fractions of a wavelength until the entire array functioned as a single, seamless mirror. By late January 2022, a month after launch, every single deployment had succeeded. All 344 single-point failures had been navigated without incident. The telescope was open, aligned, cooling, and cruising toward its final destination. Engineers who had spent decades working on the project, some of whom had started as graduate students and were now grey-haired senior scientists, allowed themselves for the first time to believe it was actually going to work. And where it was heading was a place as strange and elegant as the telescope itself. You are drifting along nicely now, and so is the telescope. Picture it out there, this golden, alien-looking structure gliding silently through the void, its sunshield spread wide like the sail of some impossible ship, its mirror gleaming with that impossibly thin layer of gold. It is heading somewhere very specific, a point in space that sounds like it was named by a 19th century mathematician, because it was Lagrange point 2, L2 if you're feeling casual about it, and the story of why Webb needs to be there is one of those beautiful intersections of celestial mechanics and practical necessity that makes you appreciate just how cleverly humans can exploit the geometry of the cosmos. In the late 18th century, a French-Italian mathematician named Joseph Louis Lagrange was working on a problem that had tormented physicists for generations, the three-body problem. How do you predict the motion of three objects all pulling on each other with gravity simultaneously? The general answer is that you cannot, not with a neat closed-form solution anyway, and this remains one of the great unsolved challenges in classical mechanics. Scholars still argue about the best numerical approaches to approximate three-body interactions, and entire academic careers have been built on increasingly sophisticated attempts to tame the chaos. But Lagrange found something elegant hiding inside the mess. He identified 5 special points in the orbital system of any two massive bodies, say, the Earth and the Sun, where a small third object can maintain a stable or semi-stable position relative to both. These are the Lagrange points, numbered L1 through L5, and they are essentially gravitational sweet spots where the pulls of the two larger bodies and the centrifugal force of orbital motion all balance out. L2 is the one that matters for Webb. It sits about 1.5 million kilometers from Earth, directly opposite the Sun, meaning that if you draw a line from the Sun through the Earth and keep going, you hit L2. At that point, an object orbits the Sun with the same period as the Earth, effectively keeping pace with our planet as it swings around its yearly circuit. From Webb's perspective at L2, the Sun, the Earth and the Moon are all in roughly the same direction, which means the sunshield can block all 3 sources of heat and light simultaneously. One shield, 3 problems solved. It is the kind of engineering elegance that makes you want to slow clap. But here is what makes L2 both perfect and slightly haunting. It is far, really far. The Moon, humanity's only other major destination in space, is about 384,000 kilometers away. L2 is roughly 4 times farther. When the Apollo astronauts had a crisis, mission control could talk to them with only a slight delay, about 1.25 seconds each way. Communication with Webb at L2 has a delay of about 5 seconds, which is manageable, but the real issue is not communication, it is access. No spacecraft currently in operation can send astronauts to L2. No repair mission is coming. No shuttle crew is going to float up to Webb with a toolkit and a can-do attitude, the way they did with Hubble 5 separate times between 1993 and 2009. This means that every component on Webb has to work, and it has to keep working, with no possibility of human hands ever touching it again. The telescope was tested exhaustively on the ground. Thermal vacuum chambers, vibration tables, acoustic tests, deployment rehearsals. But there is a peculiar loneliness to an instrument that will never be serviced. It is out there on its own, a mechanical orphan performing flawlessly in an environment that would kill you in about 15 seconds if you were exposed to it without a suit. And the cold. Let us talk about the cold, because it is central to everything Webb does. At L2, shielded from the sun by its tennis court-sized parasol, the telescope's mirrors and instruments settle to a temperature of about -233 degrees Celsius. That is roughly 40 degrees above absolute zero, the theoretical temperature at which all molecular motion ceases. At these temperatures, the beryllium mirrors contract and stabilize into their final, precise shape. The instruments become sensitive enough to detect the faintest wisps of infrared radiation drifting in from the edge of the observable universe. One of Webb's 4 instruments, MIRI, the mid-infrared instrument, built by a European consortium, needs to be even colder. It operates at -266 degrees Celsius, just 7 degrees above absolute zero. To achieve this, MIRI has its own dedicated cryocooler, a mechanical refrigerator that chills the detector to temperatures colder than the surface of Pluto, colder than the void between galaxies, colder than almost anywhere in the natural universe. There is a quirky irony in this. To see the heat signatures of the earliest cosmic objects, you have to make your detector one of the coldest things in existence. You have to become colder than the universe in order to listen to it. Here's a fringe detail that rarely makes it into mainstream coverage. L2 is not perfectly stable. It is what physicists call a saddle point, stable in one direction but unstable in another, like a marble balanced on the ridge of a horse saddle. Left alone, Webb would slowly drift away from L2 and wander off into a useless orbit. So the telescope performs small station-keeping burns every few weeks, firing tiny thrusters to nudge itself back into position. Those thrusters run on hydrazine fuel, and Webb launched with a finite supply. The original mission was designed for a minimum of 5 years, with fuel for 10 if everything went well. But remember that impeccable Ariane 5 launch on Christmas morning? It was so accurate, so perfectly on target, that Webb used far less fuel than expected for its initial course corrections. Current estimates suggest the telescope may have enough fuel for 20 years or more. 20 years of infrared eyes staring into the oldest corners of the universe. 20 years of data streaming back from a point in space so far away that if Webb could see Earth, our planet would be a pale speck lost in the sun's glare. 20 years of a golden mirror, colder than almost anything in creation, catching photons that have been travelling since the universe was an infant. And in the summer of 2022, those photons finally arrived as images. The first images, the ones that made the world gasp. But before we get to those images, and trust me, they are worth the wait, you need to understand something about the light Webb is designed to capture. Because without this piece of the puzzle, the pictures are just pretty colours. And what makes them extraordinary is not how they look, but what they mean. You are familiar with visible light. It is the narrow band of electromagnetic radiation that your eyes evolved to detect. The rainbow spectrum from violet through blue, green, yellow, orange, to red. It is a tiny sliver of the full electromagnetic spectrum, which stretches from gamma rays at the short wavelength high energy end all the way to radio waves at the long wavelength low energy end. Visible light sits somewhere in the middle, a slim window through which your species has been peering at the universe for a few 100,000 years. Everything you've ever seen, every sunset, every face, every star glittering above you right now, has been delivered to your brain by this one narrow band. Hubble was built primarily to see in this band, along with some near-ultraviolet and near-infrared capability, and it did extraordinary things with it. But there is a fundamental problem with visible light when you're trying to look at the oldest, most distant objects in the cosmos, and that problem is the expansion of the universe itself. In 1929, an American astronomer named Edwin Hubble, yes, the same Hubble the telescope is named after, confirmed something that would reshape all of cosmology. By studying the light from distant galaxies, he noticed that the farther away a galaxy was, the more its light was shifted toward the red end of the spectrum. This red shift, as it became known, was not caused by the galaxies themselves moving through space like cars on a highway. It was caused by space itself stretching. The fabric of the universe is expanding, and as it expands, the wavelength of any light travelling through it gets stretched along with it. A photon that started its journey as blue light billions of years ago arrives at your detector as red light, or if it has travelled far enough, as infrared light, wavelengths longer than your eyes can see, longer than Hubble could efficiently capture. This is the key. The oldest light in the universe has been stretched so much by cosmic expansion that it has shifted entirely out of the visible spectrum and into the infrared. It is still there, still carrying information from the dawn of time, but it has become invisible to any telescope designed for visible light. It is like trying to hear a conversation that has been pitched down below the range of human hearing. These sound waves exist. The information is intact, but your ears simply are not built to receive it. Webb's ears, so to speak, are built for exactly this. Its instruments are optimized for near-infrared and mid-infrared wavelengths, the precise range where the most ancient, most red-shifted light ends up after travelling for 13 billion years through an expanding universe. When Webb looks at a patch of sky, it is not seeing the same things Hubble saw. It is seeing through and beyond them, past the dust clouds that block visible light, past the redshift barrier that hid the earliest galaxies, all the way back to an era when the universe was less than 2% of its current age. And there is another advantage to infrared that is almost poetic in its elegance. Dust, cosmic dust, the fine particulate matter that permeates galaxies and nebulae, is opaque to visible light but largely transparent to infrared. If you have ever seen Hubble's famous image of the pillars of creation in the Eagle Nebula, those towering columns of gas and dust look solid, almost architectural, like cathedral spires carved from smoke. But point an infrared telescope at the same structures and the pillars become translucent. You can see through them. You can see the baby stars forming inside, the dense knots of gas collapsing under gravity, the earlier stages of stellar birth hidden behind curtains that visible light cannot penetrate. It is like switching from looking at a fogged window to suddenly having X-ray vision. The universe does not change. Your ability to perceive it does. Scholars in the history of science still argue about who deserves the most credit for recognizing the potential of space-based infrared astronomy. The concept was discussed as early as the 1960s, but the technology did not exist to make it practical. Earlier infrared space telescopes, the Infrared Astronomical Satellite in 1983, the Spitzer Space Telescope launched in 2003, proved the concept and delivered remarkable science, but they were limited in size and sensitivity. Webb represents the culmination of decades of incremental progress, a machine that could not have existed without every mission that came before it, each one pushing the technology a little further, each one revealing a little more of what was hiding in the infrared dark. Here is a quirky tidbit that captures how different infrared vision really is. If you could see in mid-infrared the way MIRI can, the world around you would look utterly alien. People would glow like lanterns. Your body emits peak thermal radiation at a wavelength of about 10 micrometers, which is smack in the middle of MIRI's detection range. Walls, furniture, the ground beneath your feet, everything with a temperature above absolute zero would be radiating and you would see it all. The darkness you perceive at night is not really dark. It is flooded with infrared light. You're just not equipped to notice. Webb is equipped. And when it turned that equipment toward the deep cosmos for the first time, it did not just confirm what astronomers expected to find. It found things that should not have been there. Objects so massive, so mature, so fully formed at such an early epoch that the standard models of cosmic evolution stuttered and stalled. The universe, it turned out, had been busy much earlier than anyone thought, assembling galaxies with a speed and efficiency that our best theories could not explain. Those first images were about to land on the desk of a president, in the inboxes of thousands of scientists, and on the screens of millions of people around the world who had no idea that a photograph could be terrifying. It is July 11th, 2022, and you are watching a live broadcast from the White House. This is not a typical presidential event. There are no policy announcements, no press conferences about legislation or economic indicators. Instead, the President of the United States, Joe Biden, 80 years old, standing behind a podium, is holding up a photograph. His hands are steady, but his expression carries something you do not often see on the face of a career politician. It looks like genuine awe. The photograph is small in his hands, but what it contains is not small at all. It is the first deep field image from the James Webb Space Telescope, a patch of sky designated SMA CS0723, and within that patch, an area of sky, again, that you could cover with a grain of sand held at arm's length. There are thousands of galaxies, not stars, galaxies, some of them appearing as they were over 13 billion years ago, their light warped and stretched by the gravity of a massive galaxy cluster sitting between them and the telescope. The image is awash in colour, deep oranges, electric blues, ghostly whites, and threaded through it all are delicate arcs of light, curved like the brushstrokes of some cosmic calligrapher. Those arcs are gravitational lensing, and they are one of the most visually stunning confirmations of Einstein's general theory of relativity that you will ever see. The idea is this: a massive object, in this case, a cluster of galaxies called SMAC 0723, located about 4 billion light-years away, warps the fabric of space-time around it so severely that light from even more distant galaxies behind it gets bent, magnified, and distorted as it passes through the warped region. The result is that background galaxies appear as elongated arcs, smeared across the sky like reflections in a funhouse mirror. Some galaxies appear multiple times in the same image, their light taking different paths around the lensing cluster and arriving at the telescope from slightly different angles. Einstein predicted this effect in 1915, and the first observation of gravitational lensing of a distant galaxy was confirmed in 1979, but Webb's image of SMAC 0723 was the most detailed, most deeply resolved gravitational lensing image ever produced. The clarity was breathtaking. Individual galaxies that appeared as vague smudges in Hubble's deepest images were now resolved into spiral arms, cores, companion satellites. The universe was being seen in a fidelity that no human eye, no previous instrument, had ever achieved. The next day, July 12th, NASA released the full batch of Webb's first images, and the scientific community collectively lost its composure in the most dignified way possible. There was the Carina Nebula, a vast stellar nursery where new stars are being born inside mountains of gas and dust, its edge lit up like a cliff face at sunset. There was Stephan's Quintet, a compact group of 5 galaxies locked in a gravitational dance, their interactions stripping gas from one another in luminous streamers. There was the Southern Ring Nebula, the glowing shell of gas expelled by a dying star, revealing for the first time in Webb's infrared gaze that the system actually contains 2 stars at its centre, not one. And there was the spectrum of WASP 96b, an exoplanet roughly 1100 light-years away, whose atmosphere Webb had tasted for the first time, detecting clear signatures of water vapour. We will return to exoplanets later. They deserve their own dedicated stretch of your pillow time. But for now, just sit with the fact that a telescope parked 1.5 million kilometres from Earth analysed the atmosphere of a planet orbiting a completely different star and found water. The casualness with which that sentence can be written in the 21st century is itself a kind of miracle. Here is a detail from that week that captures the emotional magnitude of the moment. When the SMACS 0723 image was first displayed on monitors at the Space Telescope Science Institute in Baltimore, several senior scientists, people who had spent 20 or 30 years working on the Webb project, cried. Not dramatically, not theatrically, but quietly, the way people cry when something they have worked toward for most of their adult lives suddenly becomes real. One astronomer who was present later described the experience as being like hearing a child's first words after years of wondering if they would ever speak. Scholars and historians of science still argue about which of Webb's first images will be considered the most scientifically significant in the long run. The deep field grabbed the public's attention, and the Carina Nebula image became an instant icon. But the spectrum of WASP 96b may ultimately prove more transformative, because it demonstrated Webb's ability to do something Hubble never could: characterize the chemical composition of worlds orbiting other stars. That capability, quiet and technical as it sounds, is the foundation upon which the search for extraterrestrial life now rests. But the first images, as stunning as they were in some sense the appetizer. They were chosen to showcase Webb's range: a deep field, a nebula, a galaxy group, an exoplanet atmosphere. A sampler platter of cosmic wonders designed to justify the $10 billion investment to the public and to Congress. The real science, the observations that would start to shake the foundations of cosmology, came in the weeks and months that followed, when Webb began its systematic survey of the deep universe and started finding things that made no sense. Massive, fully formed galaxies sitting in an epoch where they had no business existing. Structures so mature, so luminous, so rich in heavy elements that the standard timeline of cosmic evolution simply could not accommodate them. The universe, it seemed, had not followed the script. It had skipped ahead, assembling itself with a ferocity and efficiency that left theorists scrambling for explanations. You're about to find out why those galaxies are so disturbing, and why the word impossible started appearing in the titles of peer-reviewed papers. Picture the universe as a baby. Not a human baby, obviously, but the metaphor works well enough if you're lying in the dark and willing to run with it. In the standard model of cosmology, the framework that has guided astrophysics for decades, the universe after the Big Bang was a hot, dense, nearly uniform soup of particles and radiation. There was no structure, no galaxies, no stars, no planets. Just an expanding fog of hydrogen and helium, cooling gradually as space itself stretched outward. Over hundreds of millions of years, gravity began to pull the slightly denser regions of this fog together, forming the first small clumps of matter. Those clumps merged into larger clumps. Those larger clumps attracted more gas, ignited the first stars, and slowly, very slowly, assembled into the earliest primitive galaxies. This is called hierarchical assembly, and it is the backbone of our understanding of how cosmic structure formed. Small things merge into bigger things, which merge into even bigger things, like snowflakes accumulating into snowballs and snowballs compacting into boulders. The process takes time, a lot of time. The first galaxies, according to this model, should have been small, irregular and messy, scrappy little collections of young stars still in the process of pulling themselves together. They should not have been large. They definitely should not have been organised. And they absolutely, positively should not have looked like they had been around for billions of years when the universe itself was barely a few 100 million years old. And yet, that is exactly what Webb found. In the months following the release of those first images, research teams around the world began analysing Webb's deep field data with the kind of intensity usually reserved for medical emergencies. What they found was a population of galaxies at extreme distances, meaning extreme look-back times, meaning we were seeing them as they existed in the very early universe, that were far too massive, far too bright, and far too structurally mature for their age. Some of these galaxies appeared to contain billions of solar masses worth of stars. Some displayed disk-like structures, spiral arms, even signs of chemical enrichment that implied multiple generations of stars had already lived and died within them. At a cosmic age of roughly 300 to 500 million years after the Big Bang. To put that in perspective, 300 million years sounds like a long time. It is, by human standards. But the universe is 13.8 billion years old. 300 million years after the Big Bang is like the first 4 hours of a 70-year human life. And in those first 4 hours, these galaxies had apparently already graduated college, bought a house, and started a retirement fund. They were not supposed to be there. Not like that. Not that fast. One of the earliest and most startling discoveries came from a team led by astronomer Ivo Labbe, who published a paper in early 2023 describing 6 candidate galaxies at high redshift that, if confirmed, were so massive they would violate the predictions of essentially every cosmological simulation in existence. The paper's title was measured, as academic papers tend to be, but the implications were anything but. If these galaxies truly contained the stellar mass they appear to contain, at the cosmic epoch they appear to occupy, then something fundamental about our understanding of galaxy formation was wrong. And here is where the scientific community did something admirable. It did not panic, and it did not immediately throw out the textbooks. Instead, it argued, vigorously, productively, and with an impressive amount of data. Some researchers suggested that the galaxies might not be as massive as they appeared, that their brightness could be inflated by active galactic nuclei, supermassive black holes at their centres spewing energy that mimicked the light of trillions of stars. Others proposed that the photometric redshifts, the method used to estimate the galaxies' distances based on their colour, might be wrong, placing them further away than they actually were. A few suggested entirely new physics, modifications to the standard model that would allow matter to clump faster in the early universe than previously thought. Scholars are still arguing that is the point. This is not a settled question. It is an active, evolving scientific debate that Webb has ignited, and every new observation cycle delivers more data that tilts the balance one way or another. Some of the original candidate galaxies have been confirmed through spectroscopic follow-up, which is a more precise method of measuring distance and mass than photometry alone. Others have been revised downward, their masses shrinking as better data refine the estimates, but even the revised numbers remain troublingly high. Even after accounting for every possible source of error, there are galaxies in the early universe that are bigger and more mature than they should be. Here is a quirky wrinkle that adds to the mystery. Some of these impossibly early galaxies appear to be red. Not red-shifted, actually red, in the sense that their stellar populations are dominated by older, cooler stars that emit more red light. In the early universe, you would expect galaxies to be blazing blue, with the light of hot, young, massive stars burning through their fuel at a furious rate. Finding red galaxies at cosmic dawn is like finding a retirement community in a maternity ward. It implies that star formation in these objects started even earlier than the epoch at which we are observing them, pushing the formation timeline back toward the Big Bang itself with uncomfortable insistence. The feeling among many astrophysicists right now is something between exhilaration and vertigo. The standard model of cosmology is not broken. It still explains an enormous amount of what we observe, but it is creaking at the seams in ways that cannot be ignored. Webb has opened a window into an era of the universe that was previously invisible, and what it has found through that window does not match the blueprint. The universe built itself faster than we thought possible, in ways we do not yet fully understand, and the scale of that mystery is growing with every new image Webb sends home. The galaxies keep getting older, the distances keep getting farther, and somewhere in the data, the record for the most distant object ever observed keeps falling. There is a race happening right now in astrophysics, and it is one of the strangest competitions you will ever encounter. No one is running, no one is sweating. The contestants are mostly sitting in office chairs staring at spectral plots on computer monitors, drinking institutional coffee, and sending each other emails with subject lines like re, rule, z greater than 14 candidate, thoughts? But the stakes are enormous, because the prize is the most distant object ever observed by human beings, and Webb has turned this race into a full-on sprint. To understand the race, you need to understand redshift, and specifically the shorthand that astronomers use to talk about cosmic distance. The letter Z, when an astronomer says a galaxy is at redshift Z equals 10, they mean the light from that galaxy has been stretched by the expansion of the universe to a wavelength roughly 11 times longer than when it was emitted. The higher the Z, the farther away the object is, and, crucially, the further back in time you are looking. A galaxy at Z equals 10 is being seen as it was about 13.2 billion years ago, when the universe was only about 470 million years old. A galaxy at Z equals 14, if confirmed, would be seen as it was roughly 13.5 billion years ago, when the cosmos was barely 290 million years old. Before Webb, the most distant confirmed galaxy was GN-Z11, detected by Hubble in 2016 at a redshift of approximately 11.1. That was already mind-boggling. Light from GN-Z11 left that galaxy when the universe was only about 400 million years old, and it had been travelling toward us for over 13 billion years. When that light began its journey, the Milky Way did not yet exist in its current form. The Sun would not ignite for another 8.5 billion years. The Earth was not even a concept, and yet that light persisted, crossing an expanding void for all that time, only to land on the instruments of a telescope orbiting a planet populated by creatures who had figured out how to build such a thing barely a century after discovering that other galaxies exist at all. Then Webb arrived and shattered the record almost immediately. In the first year of operations, candidate galaxies were reported at Z equals 12, 13 and beyond. Some of these were tentative, identified through photometric estimates that required spectroscopic confirmation. But even the conservative confirmed detections pushed past GNZ 11's record with startling ease. It was as if Hubble had been standing on its tiptoes trying to see over a fence, and Webb had simply walked through a door on the other side. One of the most discussed early candidates was a galaxy nicknamed Glass, Z13, tentatively placed at a redshift of approximately 13 by a team analysing data from one of Webb's early observation programs. If confirmed, it would mean we were seeing a galaxy as it existed just 300 million years after the Big Bang. The announcement generated enormous excitement and equally enormous caution. Photometric redshifts can be fooled. A dusty, reddened galaxy at a lower redshift can sometimes mimic the colours of a much more distant object. The astronomical community has been burned before by premature distance claims, and no one wanted to be the team that announced a record-breaking galaxy, only to have it reclassified as a relatively nearby interloper. But spectroscopic confirmations began rolling in through 2023 and 2024, and the records kept falling. JWST Z14-0, confirmed through the JWST Advanced Deep Extragalactic Survey, was placed at a redshift of approximately 14.32, making it the most distant spectroscopically confirmed galaxy as of its announcement. You're looking at an object as it existed roughly 290 million years after the Big Bang. The universe at that moment was about 2% of its current age, and this was not a faint, barely there smudge at the edge of detectability. It was a galaxy with a measurable physical extent, detectable luminosity, and evidence of active star formation. Something substantial was already there, already shining, in an era when the cosmos was still emerging from its primordial darkness. Here is a historical touchstone that helps frame just how rapidly this field is evolving. In 1995, the year of Hubble's Deep Field, remember that grain of sand-sized patch that revealed 3,000 galaxies? The most distant known galaxy was at a redshift of about 4.7. In less than 30 years, that record has tripled. The pace of discovery is not linear. It is accelerating, driven by instruments of increasing power peering into depths of increasing obscurity, and Webb is the engine of the current acceleration. Scholars debate whether we're approaching a practical observational limit, a redshift beyond which galaxies simply did not yet exist because the universe had not had time to form them, or whether Webb will continue finding surprises even deeper. Some theoretical models suggest the very first stars, the so-called population 3 stars, made entirely of hydrogen and helium with no heavier elements, could have formed as early as 100 million years after the Big Bang, corresponding to redshifts of Z equals 20 or higher. Webb may or may not be sensitive enough to detect them, but the possibility hangs in the air like a dare. And here is a quirky detail that captures the human side of this cosmic race. When a team believes they have identified a new distance record galaxy, the paper goes through peer review, which can take months. During that time, another team may submit their own candidate at an even higher redshift. The result is a peculiar slow-motion competition, where the lead changes not in real time, but in the glacial rhythm of academic publishing. Scientists have joked that the record for the most distant galaxy now has less permanence than a sandcastle at high tide. Somewhere out there, photons even older than those from JD's GSC 14-0 are still drifting through the void, stretched beyond recognition, carrying whispers from an era so early that the universe had not yet learned how to be transparent. That era has a name, and it is one of the most evocative phrases in all of cosmology. The Cosmic Dark Ages. Say it slowly and let it sit in your mind for a moment, because it is one of those rare scientific terms that sounds exactly as dramatic as the thing it describes. The Cosmic Dark Ages refer to a period in the universe's history that began roughly 380,000 years after the Big Bang and lasted for perhaps 100 or 200 million years, an epoch during which the entire cosmos was, quite literally, dark. No stars, no galaxies, no light sources of any kind. Just an expanding, cooling ocean of neutral hydrogen gas, utterly black, filling every corner of existence with a silence so complete it makes the quietest room you have ever been in sound like a rock concert. To understand how the universe arrived at this state, you need to rewind to the very beginning, or at least to the earliest moments we can meaningfully describe. In the first few 100,000 years after the Big Bang, the universe was so hot and so dense that matter and radiation were locked together in a blinding, opaque plasma. Photons could not travel freely because they kept colliding with charged particles, protons and electrons zinging around at tremendous speeds. The universe was like the inside of a furnace, glowing white hot in every direction, with no structure and no transparency. Then, about 380,000 years in, the universe cooled enough for electrons to be captured by protons, forming neutral hydrogen atoms. This event is called recombination, which is a slightly misleading name because it implies the electrons and protons had been combined before and were recombining, when in fact they were combining for the first time. Physicists are aware of this naming quirk and have decided to live with it, which tells you something about the priorities of people who name cosmic epochs. When recombination happened, the universe suddenly became transparent. Photons were free to travel without being scattered, and they have been travelling ever since, stretched by the expansion of the universe from their original white-hot glow into the faint microwave radiation that permeates all of space today. This is the cosmic microwave background, the oldest light in the universe, and it was first detected accidentally in 1965 by Arno Penzias and Robert Wilson, two Bell Labs engineers who initially thought the persistent static in their radio antenna was caused by pigeon droppings. They cleaned the antenna, the signal remained, and they eventually realized they were hearing the afterglow of creation itself. They won the Nobel Prize. The pigeons did not. But after recombination, after that first flash of light was released, the universe entered its dark phase. Neutral hydrogen is transparent to the cosmic microwave background radiation that was already streaming through space, but it does not produce its own visible light, and no stars had yet formed to illuminate the void. So for 100 million years or more, the cosmos sat in perfect darkness, a vast featureless expanse of hydrogen and helium gas, slowly cooling, slowly clumping under the pull of gravity, but producing not a single photon of visible light. If you could somehow transport yourself to this epoch, you would see nothing. Absolute, total, primordial blackness in every direction, stretching to infinity. This is the era that Webb is now probing, and it is doing so by looking for the light that ended the Dark Ages, the first stars and galaxies that ignited and began to burn through the cosmic fog. This transition, from darkness to light, is called the Epoch of Reionization, and it is one of the least understood chapters in the history of the universe. What happened, in broad strokes, is that the first luminous objects, whether they were massive primordial stars, early galaxies or accreting black holes, began emitting ultraviolet radiation so intense that it ionized the neutral hydrogen around them, stripping electrons from atoms and creating expanding bubbles of transparent ionized gas. Over time, these bubbles grew and merged until the entire universe was reionized, and light could travel freely once more. Scholars fiercely debate the details of this process. Did the first stars provide most of the ionizing radiation, or was it early galaxies? Did supermassive black holes contribute significantly? How patchy was the process? Did reionization happen uniformly across the cosmos, or were some regions ionized hundreds of millions of years before others? These questions have been discussed theoretically for decades, but until Webb, there was almost no direct observational evidence to constrain the answers. Hubble could see galaxies from the tail end of reionization, but the heart of the process, the moment when the first bubbles of light began to punch through the neutral hydrogen fog, was beyond its reach. Webb is changing that. Its infrared sensitivity allows it to detect galaxies embedded in the still neutral intergalactic medium, galaxies that are actively participating in the reionization process. Some of the high redshift galaxies discovered in Webb's first year of operations appear to be surrounded by partially ionized regions, their ultraviolet output carving out local zones of transparency in the otherwise opaque universe. Astronomers are essentially watching the lights come on, one by one, in a cosmos that had been sitting in darkness for 100 million years. Here is a detail that quietly captures the strangeness of this era. During the cosmic dark ages, the universe was not empty. It was full of matter, full of energy, full of potential. Every atom that would eventually become a star, a planet, a mountain, a molecule of water in your body was already there, drifting in the dark. The raw materials for everything that exists were present from the beginning. They just had not found each other yet. The Dark Ages were not an absence. They were a pause, the universe holding its breath before the first exhale of light. And that first exhale, when it came, was not gentle. It was violent, brilliant, and transformative. The stars that ended the Dark Ages were almost certainly monsters, hundreds of times more massive than our Sun, burning at temperatures and luminosities that would make any modern star look timid by comparison. They lived fast, died young, and in their death seeded the universe with the first heavy elements, the building blocks that would eventually become rocky planets, and, on at least one of those planets, something that could look back and wonder how it all began. Webb is watching the nurseries where those first lights were kindled, and what it sees there is both beautiful and deeply humbling. You have probably seen the image even if you do not remember its name. It went viral in a way that scientific photographs rarely do, shared millions of times, printed on posters, set as phone wallpapers by people who could not explain exactly what they were looking at, but knew, instinctively, that it was important. The cosmic cliffs of the Carina Nebula. Webb's infrared portrait of a stellar nursery so vast, so sculpted, so impossibly detailed that it looked less like a photograph and more like a landscape painting by some deity with an unlimited palette and a flair for drama. What you are seeing in that image is the edge of a gigantic cavity in a nebula called NGC 3324, located roughly 7,600 light-years from Earth, in the southern constellation Carina. The cliffs are towering walls of gas and dust, several light-years tall, being eroded by the blistering ultraviolet radiation and stellar winds from hot young stars just outside the frame. The boundary between the illuminated upper region and the dark, dusty lower region is sharp and ragged, like a coastline being eaten by a luminous sea. And hidden within the dark side of those cliffs, invisible to Hubble but glowing unmistakably in Webb's infrared vision, are dozens of newborn stars, protostars technically, still cocooned inside the dense knots of gas from which they are forming. This is how stars are born, not in the clean, bright emptiness of open space, but deep inside thick clouds of molecular hydrogen and dust, regions so dense and so cold that they block all visible light. Gravity pulls the densest pockets of gas inward, compressing them, heating them, until the core reaches temperatures of about 10 million degrees Celsius and hydrogen fusion ignites. A star switches on, and in that moment, an object that was invisible becomes a furnace, pouring energy into the surrounding cloud, blowing away the cocoon of dust and announcing its existence to the universe in a blaze of infrared radiation that Webb can see with exquisite clarity. The Carina Nebula image was revelatory because it showed this process in unprecedented detail. Previous infrared telescopes, including Spitzer, had peered into stellar nurseries before, but their resolution was limited, like looking at a pointillist painting from across a museum hall. Webb brought you close enough to see the individual dots, protostellar jets, narrow beams of superheated gas blasting outward from the poles of forming stars at hundreds of kilometers per second, were visible as thin, luminous needles poking out of the dark clouds. Herbig-Haro objects, the glowing shock fronts created when those jets slam into the surrounding medium, were resolved with a sharpness that made astronomers giddy. And then there were the pillars of creation. You know this image too, or at least the original version. Hubble photographed the pillars in 1995, the same year as the Deep Field, and the image became one of the most recognizable astronomical photographs in history. 3 columns of gas and dust rising from a larger cloud in the Eagle Nebula, about 6,500 light-years away, looking like the fingers of a cosmic hand reaching upward into a greenish haze. The image was beautiful, haunting, and widely reproduced. It appeared on t-shirts, in textbooks, and in at least one dentist's office you have almost certainly visited. Webb rephotographed the pillars in October 2022, and the result was not an update so much as transformation. In Hubble's visible light image, the pillars are opaque, dark, brooding structures silhouetted against a glowing background. In Webb's infrared image, the pillars become ghostly and translucent. You can see through them. The dense cores where new stars are forming appear as bright red points, embedded within the columns, like embers glowing inside smoke. The edges of the pillars, where ultraviolet radiation from nearby massive stars is slowly boiling away the gas, glow with a delicate fiery trim. It is the same structure, the same physical object, but seen in a completely different light, literally, and the difference is staggering. Here is a historical fact that adds a bittersweet layer to the pillars. Some astronomers believe that the actual pillars of creation may have already been destroyed. A Spitzer Space Telescope observation in 2007 revealed evidence of a supernova shockwave approaching the pillars from behind, and some estimates suggest the blast may have reached and dismantled the structures roughly 6,000 years ago. But because the Eagle Nebula is 6,500 light-years away, the light showing us their destruction has not arrived yet. We may be admiring the portrait of something that no longer exists, a ghost image, preserved by the speed of light, of a structure that has already been scattered to the cosmic winds. Scholars still argue about the timing and whether the shockwave has truly reached the pillars, but the possibility itself is a beautiful, melancholy reminder that everything you see in the night sky is history. And here is a quirky detail about stellar nurseries that most people never consider. The process of star formation is spectacularly inefficient. In a typical molecular cloud, and these clouds can be tens or even hundreds of light-years across, containing enough gas to make millions of stars, only a tiny fraction of the material actually ends up in stars. Estimates vary, but something like 1 to 10% of a cloud's mass will collapse into stellar objects. The rest gets blown away by the radiation and winds of the very stars that form within it, dispersed back into the interstellar medium to drift and cool, and eventually participate in the next generation of star formation somewhere else, perhaps millions of years later. The universe, in other words, is not a tidy manufacturer. It is wasteful, chaotic, and recursive, endlessly recycling its materials through cycles of collapse and dispersal, birth and death, creation and destruction. And Webb is showing us these cycles with a clarity that makes the process feel almost intimate, as though you are peering through a window into a delivery room where suns are being born, messy and screaming and brilliant, deep inside clouds that your eyes were never meant to penetrate. But stars are only half the story Webb is telling. The other half involves the worlds that form around those stars, planets, billions of them, orbiting in the habitable zones of their parent suns, and for the first time in history, Webb can actually taste their air. Taste is the right word, even if it sounds strange applied to a planet hundreds of light years away. What Webb does when it studies an exoplanet's atmosphere is, in principle, not so different from what your tongue does when you eat something. It identifies the chemical components of the thing it is sampling. Except instead of salt or sugar, Webb is detecting carbon dioxide, water vapour, methane, and a growing list of other molecules, and instead of direct contact, it is doing it by analysing the specific wavelengths of starlight that get absorbed as they filter through an alien sky. The technique is called transmission spectroscopy, and the concept is elegant enough to explain while you're lying in the dark. Imagine an exoplanet orbiting its host star. At some point in its orbit, the planet passes directly between the star and the telescope, an event called a transit. During a transit, a thin ring of the planet's atmosphere is backlit by the star, and starlight passes through that atmospheric rim on its way to Webb's detectors. Different molecules absorb different wavelengths of light. Water vapour leaves a specific fingerprint. Carbon dioxide leaves a different one. Methane, ammonia, sodium. Each molecule imprints a unique pattern of absorption lines onto the starlight, and by comparing the spectrum of the star during a transit with the spectrum when no planet is in the way, Webb can subtract one from the other and reveal the chemical signature of the atmosphere itself. It is, in essence, reading the recipe of an alien sky from over 1,000 light-years away. And Webb did it almost immediately. The first atmospheric detection announced during those July 2022 first results presentations was WSP-96b, a hot gas giant orbiting a sun-like star roughly 1,150 light-years from Earth. Webb's near-infrared imager and slitless spectrograph captured the unmistakable absorption signature of water vapour in WSP-96b's atmosphere, along with evidence of clouds and haze. Now, WSP-96b itself is not the kind of planet anyone expects to harbour life. It is a bloated, scorching hot Jupiter-class world, tidally locked to its star, with atmospheric temperatures exceeding 1,000 degrees Celsius. But that was not the point. The point was proof of concept. If Webb could detect water vapour in the atmosphere of a hot Jupiter, it could do the same for smaller, cooler, rockier worlds. The kind of worlds where water might actually pool on surfaces, where clouds might carry rain, where chemistry might do something genuinely interesting. And it did not take long. In 2023, a team of researchers announced the detection of carbon dioxide in the atmosphere of a rocky exoplanet for the first time. The target was a world in the TRAPPIST-1 system, a collection of 7 roughly Earth-sized planets orbiting a small, cool red dwarf star about 40 light-years away. The TRAPPIST-1 system had been a priority target for Webb since before launch, because several of its planets orbit within or near the habitable zone, the region around a star where liquid water could theoretically exist on a planet's surface. Finding carbon dioxide on one of these worlds was not evidence of life, but it was evidence of an atmosphere, and that alone was significant. Many models had predicted that red dwarf stars, which are prone to violent flares and intense ultraviolet radiation, might strip their planet's atmospheres entirely, leaving them as barren, airless rocks. The detection of CO2 suggested that at least some of these worlds had managed to hold on to their atmospheric envelopes. Then came the molecule that really got people talking, dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by phytoplankton in the oceans. It is the compound largely responsible for the smell of the seaside, that briny, slightly sulphurous tang you catch when the wind blows off the water. When a team analysing Webb data from the exoplanet K2-18b reported a tentative detection of dimethyl sulfide in its atmosphere, the scientific community took a sharp collective breath. K2-18b is a fascinating world in its own right. It orbits in the habitable zone of its star, about 120 light-years from Earth, and it is classified as a sub-Neptune, larger than Earth but smaller than Neptune, with a mass roughly 8.5 times our planet's. Webb's spectra revealed clear detections of methane and carbon dioxide in its atmosphere, along with an intriguing absence of ammonia. This chemical combination is consistent with what some researchers call a Hycean world, a planet with a hydrogen-rich atmosphere overlying a global liquid water ocean. The dimethyl sulfide detection was tentative and has not been confirmed, and the team was careful to note that non-biological processes could potentially produce the molecule under the right conditions. Scholars vigorously debate whether K2-18b's atmospheric chemistry can be reliably interpreted with current data, and whether Hycean worlds are even physically plausible environments for life. But here is the thing that matters, the thing you can carry with you as your eyelids grow heavier. For the first time in human history, we have an instrument capable of detecting molecules in the atmospheres of planets orbiting other stars that could, in principle, be produced by living organisms. We have never had that before. Every previous generation of astronomers could only speculate about what alien atmospheres might contain. Webb can measure it. Not perfectly, not conclusively, not yet with the sensitivity to make definitive claims about biology. But the door is open, and it is open wider than it has ever been. Here is a quirky historical footnote that ties this all together. The very concept of spectroscopy, analysing light by splitting it into its component wavelengths, was pioneered in the early 19th century by Joseph von Fraunhofer, a Bavarian glassmaker who noticed dark lines in the spectrum of sunlight. He catalogued hundreds of these lines without fully understanding what caused them. It was not until decades later that scientists realised those lines were absorption signatures of chemical elements in the sun's atmosphere. Fraunhofer, in a sense, was the first person to taste a star. He just did not have the language to describe what he had done. 2 centuries later, his technique is being used to taste the atmospheres of worlds orbiting distant suns, searching for the chemical fingerprints of life itself. You're still awake, which means either you are genuinely fascinated, or you are the kind of person who cannot fall asleep until you know whether we have found aliens. Fair enough. Let us talk about what it would actually take for Webb to find convincing evidence of life on another world, because the answer is both closer than you think and more complicated than you hope. The concept at the centre of this search is the biosignature, a chemical or physical feature of a planet's atmosphere that is best explained by the presence of living organisms. On Earth, the most obvious biosignature is oxygen. Our atmosphere is roughly 21% molecular oxygen, and virtually all of it is produced by photosynthetic organisms, plants, algae, cyanobacteria. Without life continuously replenishing it, oxygen would react with surface minerals and volcanic gases and disappear from our atmosphere within a few million years. If you were an alien astronomer pointing your telescope at Earth from 100 light-years away, and you detected a thick oxygen atmosphere alongside methane, a gas that reacts readily with oxygen and should not coexist with it in significant quantities unless something is actively producing both, you would have strong circumstantial evidence that something biological was happening on that blue dot. This is the logic driving the biosignature hunt. Find a planet in the habitable zone, detect its atmosphere, look for gases that should not coexist in chemical equilibrium unless life is maintaining them. The combination of oxygen and methane is considered the gold standard, but other combinations are also compelling. Carbon dioxide alongside methane in a hydrogen-rich atmosphere, for instance, is the scenario that K2-18b's data hints at, and it has generated enormous theoretical interest precisely because it is difficult to produce through purely geological or chemical processes on a world with a liquid water surface. But here is where the complexity kicks in, and where you start to appreciate why scientists are both thrilled and painfully cautious. Biosignatures are not proof of life. They are statistical arguments. Every potential biosignature has at least one hypothetical abiotic explanation, a way it could be produced without biology. Oxygen can be generated by the photodissociation of water vapor in a planet's upper atmosphere, where ultraviolet light splits water molecules and hydrogen escapes to space, leaving oxygen behind. Methane can be produced by geological processes like serpentinization, where water reacts with certain iron-rich minerals in a planet's crust. Even dimethyl sulfide, that tantalizing molecule detected tentatively on K2-18b, could conceivably be produced by photochemical reactions in the right atmospheric conditions, though no one has demonstrated a convincing abiotic pathway yet. The challenge, then, is not merely to detect a single molecule, but to build a comprehensive chemical portrait of an atmosphere that is so difficult to explain without biology that the abiotic alternatives become implausible. Scientists call this the smoking gun threshold, and we have not reached it yet. What Webb has done is bring us closer to that threshold than any previous instrument, by demonstrating that it can detect the relevant molecules at the relevant concentrations on the relevant types of planets. The gun exists. We are looking for the smoke. There is a scholarly debate raging right now about how many transits of a given planet Webb needs to observe before it can build a reliable atmospheric spectrum. Each transit provides a small amount of signal, and the signal is noisy. Contaminated by stellar variability, instrumental artifacts, and the sheer faintness of the atmospheric absorption features compared to the overwhelming brightness of the host star. For a large planet like K2-18b, a handful of transits may suffice to detect major atmospheric components. For a truly Earth-sized planet in the habitable zone of a Sun-like star, the atmospheric signal is so tiny that Webb may not be able to detect it at all, even with dozens of transits. This is a fundamental limitation, not of Webb's design, but of the technique itself, and it means that the first convincing biosignature detection, if it comes from Webb, is most likely to come from a sub-Neptune or super-Earth, orbiting a small dim red dwarf star, where the planet-to-star size ratio is more favourable. Here is a historical fact that adds a layer of irony to the search. In 1996, a team of NASA scientists announced that they had found evidence of fossilized microbial life in a Martian meteorite called ALH 84001, a chunk of a rock blasted off the surface of Mars by an ancient impact and eventually recovered from the Allen Hills region of Antarctica. The announcement was made at a press conference attended by the sitting president, and it generated global headlines. Subsequent analysis, however, cast serious doubt on the biological interpretation. The structures that had been identified as microfossils could be explained by non-biological mineral processes, and the consensus shifted away from the life hypothesis over the following years. Scholars still argue about ALH 84001. A small minority of researchers maintain that the biological explanation has not been definitively ruled out. But the episode serves as a cautionary tale about the dangers of premature announcements in astrobiology. Nobody wants to repeat that experience with Webb. The stakes are too high and the scrutiny too intense. If a team announces a biosignature detection, it will face the most rigorous peer review in the history of science, and rightly so. The claim that we have found evidence of life beyond Earth would be, by almost any measure, the most significant scientific discovery ever made. It would reshape philosophy, theology, and humanity's understanding of its place in the cosmos. It is not the kind of claim you make lightly, and yet, here is a quirky and slightly giddy truth. We are closer to that claim than we have ever been. The instruments exist, the targets are identified, the observation programs are underway. Within the next few years, Webb may deliver atmospheric data from a habitable zone rocky world that contains a combination of gases that is genuinely difficult to explain without invoking biology. It may not be definitive. It may spark decades of further study and debate. But the data will exist, and it will be real. And it will have been gathered by a golden mirror sitting in the cold dark at Lagrange Point 2, quietly tasting the air of worlds we will never visit in our lifetimes. That thought alone is enough to keep you staring at the ceiling for a while longer. But atmospheres and biosignatures are not the only impossible things Webb has found lurking in the early universe. There is another mystery, one that predates the search for life, and strikes at the very foundations of how we think the cosmos assembled itself. It involves the most extreme objects in the known universe, supermassive black holes, and Webb has discovered that they, like the galaxies we discussed earlier, seem to have shown up to the cosmic party far too early and far too large. You are familiar with the basic concept of a black hole, a region of space where gravity is so intense that nothing, not light, not matter, not information, can escape once it crosses the boundary known as the event horizon. Stellar black holes, the garden variety kind, form when massive stars exhaust their nuclear fuel and collapse under their own gravity. They are typically a few times to a few dozen times the mass of our Sun, and they are scattered throughout galaxies by the billions. Impressive but manageable. Supermassive black holes are a different beast entirely. These are monsters that sit at the centres of galaxies, containing millions to billions of times the mass of the Sun, and their gravitational influence governs the structure and evolution of their entire host galaxy. The supermassive black hole at the centre of the Milky Way, called Sagittarius A star, has a mass of about 4 million solar masses. The one at the centre of the galaxy M87, the one famously imaged by the Event Horizon Telescope in 2019, looking like a glowing orange donut, has a mass of roughly 6.5 billion solar masses. These are objects so massive that they bend space-time into a funnel from which nothing returns, and they do it on a scale that makes stellar black holes look like puddles next to an ocean. The question that has haunted astrophysics for decades is, how did they get so big? Supermassive black holes are observed in virtually every large galaxy in the present-day universe, and their masses correlate tightly with the properties of their host galaxies, bigger galaxy, bigger black hole. This correlation suggests a deep co-evolutionary relationship between galaxies and their central black holes, but the mechanism of that co-evolution is still poorly understood, and the problem gets much worse when you look at the early universe, because Webb has now found supermassive black holes at redshifts so high that there simply was not enough time for them to have grown to their observed sizes through the standard processes. The standard model of black hole growth works roughly like this. A seed black hole forms, either from the collapse of a massive star or from the direct collapse of a massive cloud of gas, and then it grows by accreting matter, pulling in gas from its surroundings, which spirals inward, heats up, and falls across the event horizon. But there is a speed limit on this process, called the Eddington limit. As matter falls in, the energy it radiates creates an outward pressure that pushes against the infalling material. There is a maximum rate at which a black hole can accrete matter before its own radiation blows its food supply away. At the Eddington limit, it takes roughly 1 billion years to grow a stellar mass seed black hole into a supermassive one. 1 billion years. That is the timescale, and Webb is finding supermassive black holes in galaxies that existed when the universe was only 500 or 600 million years old. Some candidates are even younger. The math does not work. Even if a seed black hole formed from the very first generation of stars, the massive, short-lived population 3 stars that likely appeared around 100 or 200 million years after the Big Bang, there's not enough time for it to grow to 1 billion solar masses by the epoch at which Webb is observing it. Not at the Eddington limit, not even close. This has sent theorists scrambling for alternatives. One proposal involves direct collapse black holes. The idea that in certain rare conditions in the early universe, massive clouds of primordial gas could collapse directly into black holes with masses of 10,000 to 100,000 solar masses, skipping the intermediate step of star formation entirely. These heavy seeds would have a significant head start, requiring less time to grow to supermassive scales. Another proposal suggests that early black holes could have exceeded the Eddington limit through episodes of super-Eddington accretion, perhaps during chaotic mergers of gas-rich proto-galaxies where the normal feedback mechanisms were overwhelmed. Scholars are deeply divided on which scenario, if any, is correct, and Webb's data has only intensified the debate. A particularly striking discovery came from observations of a galaxy called GN-Z11, the same galaxy that held Hubble's distance record, remember, where Webb detected spectral signatures consistent with an active galactic nucleus, a supermassive black hole furiously accreting matter at a redshift of about 10.6. The implied black hole mass was staggering for such an early epoch, and the detection suggested that supermassive black holes were not just present in the early universe, but were already actively shaping their host galaxies through energetic feedback processes. Here is a quirky detail that underscores how strange these objects are. A supermassive black hole with a mass of 1 billion solar masses has an event horizon roughly the size of our solar system. You could fit the orbits of all 8 planets inside it, and yet the black hole itself, according to general relativity, has no physical size. All that mass is compressed into a singularity of infinite density at its centre. The event horizon is not a surface but a boundary, a point of no return defined purely by geometry. It is one of those concepts that your brain can process as words, but refuses to accept as reality, like being told that your house has always been a hologram. Webb cannot see black holes directly, of course. No telescope can. But it can see the fireworks they produce, the blazing accretion disks, the relativistic jets, the ionized gas clouds swirling at fractions of the speed of light. And those fireworks burning at the dawn of time are telling us that the universe built its most extreme objects on a timeline that our theories cannot yet explain. And those black holes are not the only invisible presence reshaping our understanding of the cosmos. There is something out there that outweighs every star, every planet, every black hole, every cloud of gas, every grain of cosmic dust combined, and we cannot see it. We have never seen it. No telescope, no instrument, no detector of any kind has ever directly observed it, and yet we know it is there, with a certainty that borders on the absolute, because without it, The universe as we observe it makes no sense. It is called dark matter, and it constitutes roughly 27% of the total mass energy content of the cosmos. The ordinary matter you're made of, the atoms, the molecules, the protons and neutrons and electrons that compose your body, your bed, the Earth, the stars, accounts for a mere 5%. You are quite literally made of the minority ingredient. The story of dark matter begins in the 1930s, when a Swiss-American astronomer named Fritz Zwicky was studying the Coma Cluster, a dense collection of over 1,000 galaxies about 320 million light-years away. Zwicky measured the velocities of galaxies within the cluster and realized that they were moving far too fast. Based on the visible mass of the cluster, the total light output of all its stars, there was not nearly enough gravitational pull to keep those galaxies bound together. They should have flown apart long ago, scattered into the void like marbles released from a bag, but they had not. Something unseen was holding them together, providing the extra gravitational glue that the visible matter could not account for. Zwicky called it Dunkel Materie, dark matter, and then the scientific community promptly ignored him for about 40 years because he had a reputation for being, shall we say, difficult to work with. The idea was resurrected in the 1970s by astronomer Vera Rubin, who found the same problem at the scale of individual galaxies. By measuring the rotation curves of spiral galaxies, how fast stars orbit at different distances from the galactic center, she discovered that stars in the outer regions were moving just as fast as stars near the center. This flatly contradicted what you would expect if only visible matter was present. In a galaxy governed solely by its visible stars and gas, outer stars should orbit more slowly, the same way outer planets in our solar system orbit the Sun more slowly than inner ones. The fact that they did not meant that galaxies were embedded in vast halos of invisible mass, extending far beyond the visible disk, providing gravitational support that kept the outer stars racing along at unexpected speeds. Since then, the evidence for dark matter has become overwhelming. It shows up in the cosmic microwave background, in the large-scale distribution of galaxies, in the dynamics of galaxy clusters, and, here is where Webb enters the story, in the patterns of gravitational lensing that Webb captures in its deep field images. Remember those beautiful arcs of light in the SMA CS 0723 image, the ones Joe Biden held up at the White House? Those arcs are created by the gravitational lensing of background galaxies by a foreground cluster, and the precise shape, position, and distortion of each arc depends on the distribution of mass in the lensing cluster, not just the visible mass, the total mass, including dark matter. By mapping the arcs in exquisite detail, astronomers can work backward and reconstruct the distribution of dark matter within the cluster, creating what amounts to an invisible sculpture rendered visible through its gravitational fingerprints. Webb's resolution and sensitivity have elevated this technique to an entirely new level. Pre-Webb lensing maps were coarse. They could identify large concentrations of dark matter, but could not resolve fine structure within those concentrations. Webb's deep fields, with their razor-sharp arcs and multiply-imaged background galaxies, allow for dark matter maps of unprecedented detail. And some of those maps are raising uncomfortable questions. In several cluster lensing analyses, the dark matter distributions inferred from Webb data do not perfectly match the predictions of the standard cold, dark matter model, the reigning theoretical framework that has successfully explained large-scale cosmic structure for decades. The discrepancies are subtle, appearing in the concentration profiles of dark matter halos and in the substructure within clusters, but they are persistent enough to attract serious attention. Some researchers suggest the discrepancies could be explained by tweaking the properties of dark matter itself. Perhaps it is not perfectly cold and collisionless as the standard model assumes, but has some degree of self-interaction that causes it to behave differently in dense environments. Scholars are engaged in a lively and ongoing debate about whether these anomalies represent genuine cracks in the cold dark matter paradigm, or whether they are artifacts of observational systematics and modelling assumptions. The data is still accumulating, and no one is ready to overthrow the standard model on the basis of a few lensing maps. But the pattern is suggestive, and Webb is providing the kind of high-precision data that could, in principle, distinguish between competing dark matter models in a way that was previously impossible. Here is a quirky thought experiment that captures the strangeness of dark matter's role in the universe. If you could magically remove all the dark matter from the cosmos, galaxies would fly apart, clusters would dissolve, and the large-scale filamentary structure of the universe, the cosmic web, that vast network of galaxy-studded threads, separated by enormous voids, would unravel. The universe you know, the one with spiral galaxies and elliptical galaxies and clusters and superclusters arranged in that beautiful web-like architecture, exists only because an invisible substance that we cannot directly detect is holding it all together. The visible universe is a decoration draped over a skeleton you cannot see. And here is the truly humbling part. Dark matter is only 27%. The remaining 68% of the universe's mass energy content is something even more mysterious. A force that is not pulling things together but pushing them apart, accelerating the expansion of the universe itself, growing stronger as space expands, and posing what many physicists consider the deepest unsolved problem in all of fundamental physics. It has an appropriately dramatic name, and Webb is making it even more puzzling than it already was: dark energy. Two words that sound like they belong on the cover of a science fiction novel, but instead sit at the centre of the most profound crisis in modern cosmology. Dark energy is the name given to whatever is causing the expansion of the universe to accelerate. Not just continue, not just coast, but actively speed up, like a car pressing harder on the gas pedal with every passing second. It was discovered in 1998 by two independent research teams studying distant Type 1 supernovae, exploding white dwarf stars whose intrinsic brightness is well understood, making them reliable cosmic distance markers. Both teams expected to find that the expansion of the universe was slowing down, gently decelerating under the collective gravitational pull of all the matter it contains. Instead, they found the opposite. The expansion was getting faster. The universe was running away from itself. The discovery was so unexpected, so counterintuitive, that the team leaders initially assumed they had made an error. They checked their data, rechecked it, checked it again, and then sat quietly with the realization that something fundamental about the universe had been missed. Saul Perlmutter, Brian Schmidt, and Adam Rees shared the 2011 Nobel Prize in Physics for the discovery, and in the decades since, dark energy has become the elephant in every cosmological living room, an entity that constitutes roughly 68% of everything that exists, and yet has no accepted physical explanation. Nobody knows what dark energy is. That sentence deserves to be repeated because it is genuinely staggering in its implications. The majority ingredient of the universe, the thing that dominates the cosmic energy budget, that governs the ultimate fate of all matter and structure, is completely unknown. The most popular theoretical candidate is the cosmological constant, a term that Einstein originally introduced into his equations of general relativity in 1917 to keep the universe static. He later called it his greatest blunder after Hubble's discovery of cosmic expansion seemed to render it unnecessary. But the 1998 supernova results resurrected the cosmological constant as a possible explanation for the accelerating expansion, reinterpreting it not as a fudge factor, but as a genuine property of empty space, a vacuum energy that permeates all of existence and exerts a repulsive gravitational effect. The problem is that when physicists try to calculate the expected value of vacuum energy from quantum field theory, they get a number that is roughly 120 orders of magnitude larger than what is observed. That is not a small discrepancy. That is the worst prediction in the history of physics, a mismatch so colossal that it suggests either our understanding of quantum mechanics or our understanding of gravity, or both, is fundamentally incomplete. Some scholars consider this the cosmological constant problem, and it has been called the most embarrassing calculation in theoretical physics. And this is where Webb wades into the crisis, because Webb is contributing to another problem that is making dark energy even more confusing, a problem known as the Hubble tension. The Hubble tension is, on its surface, a simple disagreement about a single number, the Hubble constant, which describes how fast the universe is currently expanding. There are two primary ways to measure this number. One method looks at the early universe, specifically the patterns in the cosmic microwave background, that ancient afterglow of the Big Bang we discussed earlier, which was mapped in extraordinary detail by the European Space Agency's Planck satellite. By analysing those patterns and running them through the standard cosmological model, you get a Hubble constant of about 67 kilometers per second per megaparsec. The other method looks at the local, relatively nearby universe, measuring the distances and recession velocities of galaxies using a chain of distance indicators, starting with Cepheid variable stars and Type 1a supernovae. This method, championed most prominently by Nobel laureate Adam Rees and his team, yields a Hubble constant of about 73 kilometers per second per megaparsec. 67 versus 73. The gap may sound small, but it's statistically enormous, well beyond the margin of error for either measurement, and it has persisted stubbornly through years of increasingly precise observations. If both measurements are correct, then something is wrong with the standard cosmological model. The universe is expanding faster in our local neighbourhood than the early universe data predicts it should be, and no known adjustment to the model can reconcile the two without breaking something else. Webb was expected to help resolve the tension, and in some ways it has, but not in the direction anyone hoped. One of Webb's early observation programs used its infrared instruments to recalibrate the Cepheid distance ladder, the foundational rung of the local measurement. Hubble had measured Cepheids in nearby galaxies, but its resolution was limited, and some researchers argued that crowding, the blending of Cepheid light with nearby unresolved stars, might be biasing the distance measurements and inflating the local Hubble constant. Webb, with its sharper infrared vision, could resolve individual Cepheids more cleanly and test this hypothesis. The result was deflating for anyone hoping the tension would simply go away. Webb's Cepheid measurements largely confirm the higher local value. The crowding hypothesis did not account for the discrepancy. The tension remained, perhaps even strengthened, and the cosmological community was left staring at a disagreement that increasingly looks like it might require new physics to explain. Here is a quirky footnote to this whole saga. The Hubble constant was first estimated by Edwin Hubble himself in 1929, and his original value was about 500 kilometers per second per megaparsec, nearly 7 times larger than the modern measurement. His estimate implied the universe was only about 2 billion years old, which was embarrassing even at the time because geologists had already determined that certain rocks on Earth were older than that. The history of measuring cosmic expansion is a history of getting it less wrong over time, and scholars still argue about whether the current tension represents the next correction waiting to happen, or the first crack in a paradigm that has served us well for decades. Whatever the answer turns out to be, Webb is providing the data that will eventually break the stalemate, one way or another. and the implications stretch far beyond a disagreement about numbers, because the rate at which the universe expands determines its ultimate fate, and that fate is something your mind is about to wrestle with, whether it wants to or not. Let us take a breath here, not because the science demands it, but because your brain deserves a moment to recalibrate before we do something slightly reckless, which is to try, honestly and without flinching, to comprehend the actual size of the universe, not metaphorically, not poetically, not in the soft-focus hand-wavy way that documentaries handle it when they say the universe is really, really big, and then cut to a graphic of zooming stars. We are going to sit with the numbers one at a time, and let each one settle into your bones like a stone dropping into still water. Start with the Earth. You live on a rocky sphere roughly 12,742 kilometers in diameter. If you could drive around its equator at highway speed without stopping, it would take about 17 days. That is your home. That is the entirety of the world as your ancestors knew it for tens of thousands of years. A sphere of rock and water and air that seemed, for most of human history, to be everything there was. Now step outward. The moon is about 384,000 kilometers away. Light covers that distance in roughly 1.3 seconds. When the Apollo astronauts travelled to the moon, the journey took about 3 days. The sun is about 150 million kilometers away, 1 astronomical unit in the jargon, and light from the sun takes about 8 minutes and 20 seconds to reach you. If the sun vanished right now, you would not know for over 8 minutes. You would be sitting in warmth and light that no longer had a source, blissfully unaware for 500 seconds. Jupiter, the largest planet in our solar system, orbits at an average distance of about 778 million kilometers from the sun. Light takes about 43 minutes to get there. Neptune, the outermost major planet, sits at roughly 4.5 billion kilometers. Sunlight needs over 4 hours to reach it. The Voyager 1 spacecraft, launched in 1977 and now the most distant human-made object in existence, is currently about 24 billion kilometers from Earth. It has been travelling for nearly 5 decades, and it has not yet left the gravitational influence of our Sun. At its current speed, it would take Voyager roughly 73,000 years to reach the nearest star system, Proxima Centauri, if it were heading in that direction, which it is not. Proxima Centauri is 4.24 light-years away. That means light, the fastest thing in the universe, takes over 4 years to cross the gap between our Sun and its nearest stellar neighbour. And in galactic terms, Proxima Centauri is essentially next door. It is the apartment across the hallway. The Milky Way galaxy, our galactic home, is a barred spiral disk roughly 100,000 light-years in diameter, containing somewhere between 100 billion and 400 billion stars. If you could travel at the speed of light, it would take you 100,000 years just to cross from one side of your own galaxy to the other. You would leave as one species and arrive as something unrecognizable if you arrived at all. And the Milky Way is one galaxy. One, in an observable universe that contains, by current estimates, at least 2 trillion galaxies. The nearest large galaxy to ours, the Andromeda Galaxy, is about 2.5 million light-years away. The light you see when you look at Andromeda left that galaxy when the genus Homo was just beginning to appear on the African savanna. You are literally looking at a time before modern humans existed when you glance at that fuzzy smudge in the autumn sky. Galaxy clusters, groups of hundreds or thousands of galaxies bound by gravity, span tens of millions of light-years. Superclusters, the largest gravitationally associated structures, stretch hundreds of millions of light-years. And beyond the superclusters, the universe is organised into a vast cosmic web. Filaments of galaxies and dark matter separated by enormous voids where almost nothing exists. Some of these voids are hundreds of millions of light-years across. Empty space so vast that light could cross it only over timescales that dwarf the entire history of human civilization by factors of millions. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a diameter of about 93 billion light-years, not 13.8 billion, which is the age of the universe because space has been expanding while the light was travelling, carrying distant objects farther away, even as their ancient photons made their way toward us. The edge of the observable universe is currently about 46.5 billion light-years away in every direction, receding from us faster than the speed of light. This does not violate relativity, because it is space itself that is expanding, not objects moving through space. But the practical consequence is absolute and permanent. There are regions of the universe whose light will never, ever reach us, no matter how long we wait. And here is the thought that quietly dismantles any remaining sense of cosmic importance you might be harbouring. The observable universe is almost certainly not the entire universe. It is merely the part we can see, bounded by the finite speed of light and the finite age of the cosmos. The actual universe, the totality of everything that exists, could be hundreds of times larger than the observable portion, or thousands of times larger, or infinitely large. We do not know. We may never know. Some inflationary models suggest the total universe is so much larger than the observable universe that comparing the two is like comparing a single atom to the entire observable universe itself. The portion of reality we can access, even with Webb, even with every telescope that will ever be built, might be a vanishingly small bubble in an ocean of existence that stretches beyond all comprehension. Here is a historical fact that grounds this vertigo in human experience. In 1995, astronomer Carl Sagan, in one of his last public reflections before his death, described Earth as a pale blue dot, a phrase inspired by a photograph of Earth taken by Voyager 1 from a distance of 6 billion kilometres, in which our planet appears as a tiny speck suspended in a beam of sunlight. Scholars still argue about whether Sagan's cosmic perspective promotes humility or nihilism, but the image itself is inarguable. You are on that dot. Everything you have ever known is on that dot, and Webb has just shown us how impossibly small that dot really is. So where does that leave you? Lying in the dark, wrapped in blankets on a speck of rock, orbiting an average star in the unfashionable outer arm of a galaxy that is one of 2 trillion, in an observable universe that may itself be an infinitesimal fraction of the whole. The numbers we just walked through are not abstractions, they are measurements. Webb has confirmed and extended them with a precision that previous generations of astronomers could only dream of. And yet the human brain, which evolved to track predators across savannas and remember which berries were poisonous, was never designed to hold this kind of scale. It is like asking a teacup to contain the Pacific Ocean. The vessel is not built for it. And this is where things get philosophically strange, because some physicists believe that the observable universe, everything Webb can see, everything Hubble could see, everything any telescope will ever see, might not be the only universe. It might be one bubble in an infinite froth of universes, each with its own physical constants, its own dimensionality, its own version of matter and energy and time. This is the multiverse hypothesis, and depending on which physicist you ask, it is either the most profound idea in the history of cosmology or the most spectacular waste of theoretical effort ever conceived. The multiverse is not a single theory. It is a collection of related ideas that emerge from several independent branches of physics, which is part of what makes it so persistent and so difficult to dismiss. The most well-known version comes from inflationary cosmology. the theory that the universe underwent a brief but extraordinarily rapid expansion in the first fraction of a second after the Big Bang. Inflation was proposed in the early 1980s by physicist Alan Guth, and it solved several nagging problems with the standard Big Bang model, including why the universe appears so flat, so uniform and so large. But inflation, once you take its equations seriously, has a disturbing tendency to not stop. In a scenario called eternal inflation, the inflationary process continues indefinitely in most of space, with occasional regions, pocket universes, dropping out of the inflationary state and becoming the kind of universe we observe. Each pocket universe would be causally disconnected from the others, separated by inflating space that expands faster than light, making direct observation or communication between them permanently impossible. Another version of the multiverse emerges from string theory, which predicts an enormous number of possible vacuum states, different configurations of the extra dimensions that string theory requires, each corresponding to a universe with different physical laws. The number of possible states has been estimated at roughly 10 to the 500th power, a number so large that writing it out in full would require more digits than there are atoms in the observable universe. This vast collection of possibilities is sometimes called the string landscape, and it suggests that our particular set of physical constants, the strength of gravity, the mass of the electron, the cosmological constant, is not uniquely determined by fundamental physics, but is instead one random draw from an unimaginably vast lottery. Scholars are fiercely divided on the scientific status of the multiverse. Critics argue that any hypothesis that cannot, even in principle, be observationally tested is not science, but philosophy, or worse, metaphysics dressed in mathematical clothing. If other universes are permanently inaccessible, then claiming they exist is no more scientific than claiming they do not. Proponents counter that the multiverse is not an assumption but a prediction, a logical consequence of theories like inflation and string theory that are themselves grounded in testable physics. The multiverse, they argue, is not invoked to explain away mysteries, but emerges inevitably from frameworks that were designed to explain observable phenomena. And here is where Webb quietly enters this lofty debate, not with definitive answers, but with tantalizing anomalies. Some of the observations that Webb has delivered, the impossibly early galaxies, the unexpectedly massive black holes, the stubbornly persistent Hubble tension, could, in certain theoretical frameworks, be interpreted as hints that our local cosmological parameters are not universal constants, but environmental variables that differ from one pocket universe to another. If the Hubble constant genuinely cannot be reconciled within the standard model, one possible explanation is that we are measuring a local value that differs from the global average because our region of space has slightly different properties than other regions. This is speculative, and most physicists would rightly caution against leaping to multiverse explanations when there are still conventional avenues to explore. But the whisper is there, in the data, and Webb is making it louder. Here is a quirky thought that physicists occasionally entertain in unguarded moments. If the multiverse is real, and if the number of universes is truly vast, perhaps infinite, then every possible configuration of matter and energy exists somewhere. There is a universe where the physical constants are slightly different and stars never form. There is a universe where gravity is stronger and the cosmos collapses back on itself within 1 million years. And there is a universe identical to this one in every detail, except that you decided not to listen to this video tonight and instead went to bed early. The implications of infinite repetition are dizzying, and they make most physicists uncomfortable in a way they're reluctant to discuss at conferences, but are perfectly willing to debate over drinks afterward. Here is a historical footnote that ties this all together with appropriate irony. The word universe itself comes from the Latin universus, meaning all things combined into one. It was, by definition, supposed to be everything. The idea that there might be more than one universe is, linguistically, a contradiction in terms, a concept that breaks its own name. And yet here we are, lying in the dark, seriously entertaining the possibility that everything we have ever observed, everything Webb has revealed in its gorgeous infrared gaze, everything contained within the 93 billion light-year sphere of the observable cosmos, might be a single grain of sand on a beach that stretches forever. The universe got terrifying a few sections ago. It just became something beyond terrifying. It became incomprehensible. And somehow, against all odds, the small creatures on the pale blue dot keep building telescopes and pointing them at the dark as if understanding were possible, as if the teacup could hold the ocean after all. But the teacup is not done yet. Webb is still out there, orbiting L2 in its perpetual shade, its golden mirror drinking in photons from the edge of time, and the observation programs lined up for the coming years read like a wish list drafted by every astronomer who ever squinted at the sky and wondered what was hiding just beyond the reach of their instruments. The telescope's best work, astonishing as the first few years have been, may still lie ahead. One of the highest priority targets for upcoming observation cycles is Proxima Centauri b, a roughly Earth-sized planet orbiting the nearest star to our Sun, just 4.24 light-years away. Proxima b sits in the habitable zone of its host star, a small red dwarf, and it has been the subject of intense speculation since its discovery in 2016. Is it a rocky world with an atmosphere and liquid water? Is it a barren, irradiated husk stripped bare by stellar flares? Or is it something in between? A planet with a thin, tenuous atmosphere clinging to survival in the harsh radiation environment of a red dwarf system? Webb has the spectroscopic sensitivity to begin answering these questions, and dedicated observation time has been allocated to attempt the first direct atmospheric characterization of our nearest exoplanetary neighbour. The results, whatever they turn out to be, will carry an emotional weight that transcends the data, because Proxima b is not just any exoplanet. It is the closest other world where life could theoretically exist. It is, in the most literal sense, next door. Then there is Europa, and you do not even have to leave our own solar system for this one. Jupiter's ice-covered moon has been one of the most tantalizing targets in astrobiology for decades, ever since the Galileo spacecraft provided strong evidence in the late 1990s that a vast liquid water ocean exists beneath Europa's frozen crust. That ocean, warmed by tidal heating from Jupiter's immense gravitational pull, may contain more water than all of Earth's oceans combined. And where there is liquid water, there is at least the possibility of life, not complex life, probably, but microbial life, chemotrophic organisms feeding on chemical energy at hydrothermal vents on the ocean floor, hidden beneath kilometers of ice in total darkness. In recent years, both Hubble and ground-based telescopes have detected what appear to be plumes of water vapor erupting from Europa's surface, geysers punching through cracks in the ice and spraying material from the subsurface ocean into space. If these plumes are real and persistent, they offer a potential shortcut for studying the ocean's composition without having to drill through the ice. And Webb, with its infrared spectrographs, is uniquely suited to analyze the chemical makeup of those plumes from a distance. Observation programs targeting Europa's plume activity are underway, and the results could tell us whether the ocean contains organic molecules, salts, or other compounds relevant to habitability. Scholars debate the reliability of the plume detections. Some observations have been difficult to reproduce, and the possibility that they are intermittent or spatially variable complicates the picture. But the scientific appetite for Europa data is enormous, and Webb is one of the best tools available to satisfy it. Beyond specific targets, Webb's broader scientific agenda for the coming years includes deep surveys of the epoch of reionization, that transition from the cosmic dark ages to the luminous universe we discussed earlier. The goal is not just to find individual high redshift galaxies, but to map the process of reionization itself, charting the growth and merger of ionized bubbles as the first light sources gradually burn through the neutral hydrogen fog. This is observationally brutal work, requiring long exposures and careful statistical analysis, but it addresses one of the most fundamental questions in cosmology. How did the universe emerge from darkness? There are also programs targeting the formation of the first heavy elements. The earlier stars were made entirely of hydrogen and helium, the only elements produced in the Big Bang. Every heavier element, carbon, oxygen, iron, gold, the calcium in your bones, the iron in your blood, was forged inside stars and dispersed by their explosive deaths. Webb can detect the spectral signatures of these elements in early galaxies, tracing the chemical enrichment of the cosmos over time. Some of the most exciting recent results involve the detection of nitrogen and oxygen in galaxies at redshifts above 10, suggesting that multiple generations of stars had already lived and died within these systems at astonishingly early epochs. And here is a quirky detail about Webb's operational future that adds a note of poignancy to all of this. The telescope runs on a finite supply of hydrazine fuel for its station-keeping maneuvers at L2. When that fuel runs out, Webb will slowly drift away from its orbital sweet spot and lose the precise pointing capability required for scientific observations. The original fuel budget was designed for a minimum 5-year mission with a goal of 10 years. Thanks to the exceptional accuracy of the Ariane 5 launch, current projections suggest Webb may operate for 20 years or more, but the clock is ticking. Every observation program is, in a sense, borrowing time from the future, and the scientific community is acutely aware that the window of opportunity, while generous, is not infinite. There is a historical parallel here that astronomers sometimes invoke. The Kepler Space Telescope, launched in 2009 to search for exoplanets by monitoring stellar transits, was designed for a 3.5-year primary mission. When 2 of its 4 reaction wheels failed in 2013, the mission was effectively crippled. But engineers devised a clever workaround using solar radiation pressure to stabilize the spacecraft, and Kepler continued operating in a modified mode called K2 for another 5 years. Scholars still argue about whether Kepler's extended mission produced science as impactful as its primary mission, but the lesson is clear. Space telescopes often outlive their expected lifespans, and resourceful engineers can squeeze extraordinary results from aging hardware. Webb's engineers are already thinking about how to maximize the telescope's remaining lifetime, prioritizing high-impact observations and developing strategies to conserve fuel. Every drop of hydrazine is a photon not yet captured, a galaxy not yet seen, an atmosphere not yet tasted. The universe is not going to wait for us, but as long as that golden mirror is cold and pointed at the sky, we have a chance to keep learning what it has been trying to tell us all along, and what it has been telling us is something you're now ready to sit with as your eyes grow heavy and the night deepens around you. You've come a long way tonight. Not in distance. You've not moved from your bed, your couch, your familiar corner of the world, but in perspective. You started this journey lying beneath a ceiling, and now, if you close your eyes, you can feel the depth of what hangs above it. Not just a sky, not just stars, a cosmos so vast, so ancient, so densely layered with mystery that the word universe barely contains it anymore. And all of it revealed, in sharper focus than ever before, by a golden mirror the size of a backyard trampoline, floating in permanent shadow 1.5 million kilometers from the nearest human being. let us gather the threads. You now know that before Webb, Hubble cracked the door open, that Robert Williams pointed his telescope at a blank patch of sky and found 3,000 galaxies hiding in the darkness, and that this single act of scientific stubbornness redefined humanity's understanding of cosmic abundance. You know that Webb was built over 25 years by thousands of engineers who invented technologies that did not previously exist, survived budget fights that nearly killed the project multiple times, and folded their creation into a rocket like the most consequential origami in history. You know about the Christmas morning launch, the 344 single-point failures, the 2-week deployment that kept grown adults awake at night, and the quiet triumph of every latch, every motor, every cable doing exactly what it was supposed to do in the freezing void. You know about L2, that gravitational sweet spot where Webb parks in perpetual shade, colder than almost anywhere in the natural universe, listening for photons that have been travelling since before the Earth existed. You know that infrared vision lets Webb see through dust, past the redshift barrier, all the way back to the cosmic dark ages, that epoch of primordial blackness when no stars had yet ignited and the universe sat in perfect, patient silence. You know about the cosmic cliffs of Carina, the pillars of creation made ghostly and translucent, the nurseries where suns are born screaming inside clouds of hydrogen and dust. You know that Webb has tasted the atmospheres of worlds orbiting distant stars, detected water vapour, carbon dioxide, methane, and the tantalising hint of dimethyl sulfide on a planet that might, just might, harbour conditions compatible with life. You know that the biosignature hunt is closer to a breakthrough than it has ever been, and that the instruments and techniques now exist to detect, for the first time, chemical evidence of biology beyond Earth. You know about the impossible galaxies, massive, mature, fully formed structures sitting in an epoch when the universe was barely old enough to have produced them, defying the standard models of hierarchical assembly. You know about the supermassive black holes that grew too big too fast, the redshift records that keep shattering, the Hubble tension that refuses to resolve. You know that dark matter holds the visible universe together like an invisible skeleton. That dark energy is pushing it apart with increasing ferocity, and that together they constitute 95% of everything that exists, while remaining almost entirely unexplained. You know the numbers now: 93 billion light-years across, 2 trillion galaxies, hundreds of billions of stars in each one, and all of that, all of it, might be a single bubble in an infinite foam of universes, each one as vast and as complex and as indifferent to your existence as this one. That is what Webb has revealed. Not just beauty, though the beauty is staggering. Not just data, though the data is reshaping every major theory in astrophysics. What Webb has revealed is scale. True, unfiltered, unapologetic cosmic scale. And the human response to that scale is not a single emotion, but a strange cocktail of terror, wonder, humility, and something that does not quite have a name. It is the feeling you get when you stand at the edge of something so large that your own existence becomes both insignificant and miraculous at the same time. Because here is the part that the terrifying numbers sometimes obscure. You are here. Against odds so astronomical that no mathematician would bet on them, the universe produced, on one small rocky planet, orbiting one average star in one unremarkable galaxy, a configuration of atoms capable of building a telescope, launching it into space, and using it to look back at the conditions that produced those very atoms in the first place. The universe is studying itself through you. Every photon Webb captures, every spectrum it analyzes, every image it sends home is the cosmos examining its own history through instruments built by a species that has existed for an eye blink of cosmic time and yet has managed somehow, to figure out a remarkable amount of what is going on. Scholars will argue for decades about what Webb's discoveries ultimately mean, whether they require new physics, whether they point toward a multiverse, whether they will lead us to evidence of life beyond Earth. Those debates will play out in journals and conferences and late-night conversations between researchers who care more about the truth than about being right. And Webb itself will continue its quiet work at L2, sipping hydrazine, rotating its golden eye from target to target, collecting photons that left their sources long before anyone was around to wonder where they came from. And now, slowly, gently, let the scale of it all begin to soften. Not shrink. It will never shrink. Not now that you've seen it. But soften, the way a landscape softens when the light fades and the edges blur and the details dissolve into a warm, indistinct glow. The 2 trillion galaxies are still there. The impossible black holes are still growing. The dark energy is still pushing. But you do not need to hold all of it right now. You have done enough holding for one night. Feel the weight of your body against the mattress. Notice how gravity, that same force that bends light around galaxy clusters and pulls gas into stars and holds the moon in its orbit, is gently pressing you downward, cradling you against the surface of your own small world. The same physics that governs the larger structures in the universe is holding you in bed right now, and there is something deeply, quietly reassuring about that continuity. You're not separate from the cosmos, you're made of it. The iron in your blood was forged in a supernova. The calcium in your bones was assembled in the heart of a dying star. The hydrogen in every water molecule in your body has been around since the first few minutes after the Big Bang. You are 13.8 billion years old in a sense, and tonight you learned a little more about your own history. So let the golden mirror keep its vigil in the dark. Let the photons continue their ancient journeys. Let the astronomers debate and the theorists recalculate, and the engineers squeeze a few more years from a machine that has already exceeded every expectation. You have travelled far enough tonight. The universe will still be there in the morning, vast, terrifying, magnificent, and waiting, and you will still be part of it, as you have always been, as you always will be. Your eyes are heavy now, let them close. The last image in your mind is not a number or a theory or a crisis in cosmology. It is a mirror, golden and hexagonal, turning slowly in the silence of deep space, catching light that has been falling for 13 billion years, and you are one of the only creatures in all of existence who knows what that light means. That is not terrifying. That is extraordinary. And it is yours. Sleep well, the universe is keeping watch.